all, this is Group 5A, Emily, Aishu, and Des, and we're going to go over our formal lab 2. So for our background, we're going to go over system schemas, free body force, and then just some general background information. Then we're going to move into our data section, including our tracker graphs, our results, which are providing our analysis of those graphs, and our calculations, and then our conclusion. So starting up with the background, our problem is how does the density of the liquid an object falls through affect its terminal velocity and the viscosity? We wanted to do this project to know how the density of an object affects the terminal velocity and viscosity when we drop a mass in a liquid. And we found that as the density of the liquid increased, the terminal velocity became smaller, but in the end, we didn't see a relationship between density and viscosity. So this is our system schema. We have the ball, the table, the cup of liquid with the liquid inside, and then the earth, which we're equating to the ground here. And our system is the ball, which you can see has the dashed line around it. This is our free body force. The forces stay the same, but it's just the magnitude changes. So I have the 2 free body forces of the ball in general, and then the ball as it moves through the liquid, which is the one on the right. These are energy pie charts. There's 4 of them depicting the different percentages of energy as it starts from when the ball is in the air before it hits the liquid and when it's at rest, and then all the way through when it reaches terminal velocity in the liquid. So in regards to energy and momentum conservation, the total energy of the system is conserved due to energy conservation, but the percentage of these different energies changes throughout the scenario, which is what I just talked about in the last slide. And then momentum is also conserved for the system.
So just some background info. When we're talking about viscosity, it's defined as a mass that is dropped into a fluid of some kind, and then the fluid has to go through, acts as a resistive force that slows down the velocity. And then we wrote the formula for viscosity below that. And then the N is the coefficient for viscosity, and then R is the radius of the object, and V is used to define the terminal velocity of an object. And terminal velocity is the maximum velocity that an object can have when it's falling, and it is not the same as average velocity. And for our experimental design, for the video, we filmed us dropping the ball that weighed 0.009 kg into 3 fluids of varying densities. And we did 2 trials for each of the liquids. And then we uploaded these videos to Tracker and generated position, velocity, and acceleration graphs. And then we calculated the values of the average velocity using Google Sheets. And then we also calculated the viscosity as well. And for our hypothesis, we said that as the density of the fluid the ball is dropped into increases, the velocity and viscosity would decrease. And then our model shows the ball dropping into the liquid, and then the way that we measured it using the ruler. These are our tracker and graphs for water, and the average velocity calculated for water 1 is negative 0.30281, and then the terminal velocity was calculated shown below. And then the average velocity for water 2 was pretty similar, and so was the terminal velocity. And then for both the oils, the average velocity and terminal velocity is also shown below the graphs as well. And then the tracker data for the detergent 1 and detergent 2 is shown. And then these are also the graphs.
So for our results to calculate the viscosity, we use the equation force times the mass times the terminal velocity. Since we know that the terminal velocity, the viscosity, and force of gravity are equal, and our numbers for each trial for the 3 separate liquids are shown below, as well as the average viscosity that we gathered. And so we could see that there is a slight effect of density, because when we dropped the ball into the detergent, which was very dense, it just kind of stopped moving. But when we dropped it into the water, it bounced, and that was shown by our math. These are our results from Python, and you can see that this data is a lot cleaner than that which we had in our tracker. And we did find that the density had an effect on the terminal velocity, but not on the viscosity. And we think that this is in part because of experimental design and tracking errors. And if we could do it over, we would design our experiment differently, run another trial, and our conclusions would be more certain. We quantitatively estimated our error, but we did find after a literature search that there is no direct relation between viscosity and density, which shows that our conclusions are accurate to what we see in the real world.